This is for, we're going to be looking at the common ion effect, which we have seen before. We are going to be looking at buffered solutions. We are going to be looking at solubility and pH. All right. So we're looking at the common ion effect, we're looking at buffered solutions, solubility, and pH. So, as you guys may recall, the common ion effect is when you've got your reaction system and then you try to add something and then cause its what to shift? Equilibrium. Now in this case, I thought we're just adding KF solid. I don't see KF solid up here anywhere. How is this actually going to impact that first one?
Because the K immediately dissipates into the water.
Oh, because K, prior to acids and bases, K was one of the ones that always does what, Michael?
It dissolves.
Always dissolves. And so in effect, when you have KF solid and you add it to anything that has water, it is actually going to be what and what? K positive, aqueous, and F negative aqueous. And which one of these two is represented in this equation up here?
F.
The F. So if we're adding F minus to here, and we know this goes 100%, does HF go 100% by the way, guys?
No, it's weak.
Ah, because it's weak.
It's a weakling.
So what's going to happen here now that we got all this extra F?
It's going to move it over.
It'll move to the left, right? Because remember, Le Chatelier's principle says that when you add something, where does the reaction go? The other side, away from it. What happens if you take something away? It goes towards wherever you add here or took away. Okay? So, F minus here is going to be our common ion that causes the equilibrium in the first reaction to shift, Le Chatelier, and the pH of the system to rise. Now, guys, why does the pH rise?
Because it's becoming more basic.
Well, what are we actually physically lowering? Go ahead, Thomas.
Because you're adding F minus. F minus is the base, so it's making it more basic.
No.
No?
No.
I wasn't paying attention at this point.
Okay, guys, think about it carefully. What literally is pH? A measure of
H plus ions.
H3O plus. If I add a ton of F, what is automatically going to be consumed and eliminated?
More
Removed.
H plus ions.
H plus, otherwise known as H3O plus. So if we actually are removing H3O plus from this situation.
We're reducing the molarity of the H plus, which reduces it to pH.
Exactly.
So bases.
You weren't wrong. You weren't wrong, but I wanted to grandstand on you. So you should feel honored.
So does that mean that in a nutshell, bases suck up H plus ions and acids spit them out?
Correct.
Okay.
All right. So let's look at another example here, guys. In this example, we've got NH3 reacted with water to make OH minus and NH4 plus. And we decide separately, but then into the same thing, we add NH4Cl. Ladies and gentlemen, what do we know guaranteed NH4Cl is going to do once it hits a solution that has water as its solvent? It'll dissolve because NH4 is one of our the ones that always dissolve. Solubility rules. Yes, all these answers. Yes. Okay, guys, which of these two are represented in this reaction? And when I add a lot more NH4 plus, where's this reaction going to go? And guys, incidentally, this is claiming that the pH will drop. Someone tell me, why is the pH going to drop?
Because
Go ahead,
Because
Charles.
concentration is taken away from OH minus.
And OH minus causes the pH to do what? Goes up. All right, very good, guys, very good.
Wait.
Anyone? Yes,
For the first one, did it rise or drop?
it rose. And you gotta be careful with that. That's a great point that you're kind of hitting on there, Solomon. Guys, pH, if it goes down, I know in our minds we're kind of built to think increases up, right? But with acids and bases, it depends on how you're thinking about it. But if pH is dropping, that means it's becoming much more acidic. And if the pH is rising, that means it's becoming much more basic. It's two different, it's a dichotomy. You've got two different things that are happening. Yes?
I just wanna, like, recap. So by adding NH4Cl, NH4Cl dissolves, right?
Instantly,
So
yeah.
then you add NH4 to the system, and by adding NH4, that makes the solution more acidic because it's taking away the concentration of OH minus.
Correct.
in the chalate.
Correct. Because remember, some of you might not, because of our emphasis on pH being related to which concentration? H3O plus, right, or H plus, either one is acceptable. You might be tempted to think, oh, well, this is OH, except for one problem. Guys, one of our principal techniques is to take the OH and then subtract it from what? From 14, and that gives you pH. So in effect, by adjusting OH minus, you are also affecting the pH. Yes, sir.
Will they ever expect you to know or to come up with something to add to increase it?
Maybe, but if they do, they'll probably give you a bank of things you can choose from.
Okay.
So you can kind of use process of elimination and kind of look at what they're offering you. All right, so guys, today is a day which will live in infamy. This is the day in which there's your life before you learned about buffers, and then there's your life after you learned about buffers. No. It goes uphill because it gets harder. And I'm so good. I'm so good at these jokes, aren't I, guys? All right. So buffers resist changes in pH, and the common ion effect is used to create buffered solutions. When small quantities of strong acids or strong bases are added to a buffered solution, the changes in pH are small. So the actual literal definition of a buffer is either a weak acid and its salt. And remember, guys, what's our chemistry definition of a salt? A positive and a negative that have come together, and when they're not dissolved, they're a solid, right? So what we're saying is a weak acid and then a conjugate base of that acid that's actually bonded to a positive ion and is in the form of a salt, which then you add to the solution. Now, this is important, guys. For a buffer to exist, you can't just have your weak acid solution and whatever it created by itself, okay? For a buffer to behave like a buffer and actually be a buffer, you have to have your weak acid and then separately add what? Extra conjugate base in the form of a salt that then dissolves and in concert with the weak acid becomes a buffer. And then overall the thing becomes a buffered solution. Okay? So let's recap. Can you just make a buffer with just a weak acid?
No.
No. You need to separately add a salt that contains a separate source of its
Conjugate base.
conjugate base. Okay? Now, that's not the only way to make a buffer. We can also make one by using a weak base and its salt, which will contain extra conjugate acid. Yes, sir.
So, oh god. So, a conjugate base. We'll start with the first weak acid one. So, a conjugate base is the reaction opposite of the acid. Is it possible for that base to turn back into the acid?
Yeah, that's the whole idea here. So what, guys, let me bottom line this for all of you. A buffer is simply, as we see there, a weak acid and a conjugate containing salt, or, the opposite with the base. And what happens is, if you add a strong acid or base to it, normally we would die if you had acids or bases inside you, which, shocker, you do. However, because our bodies have natural buffers, which is this, and a buffer is like a pendulum. So you hit it with a strong acid, instead of going straight to the water, and remember, if that strong acid hits water, what does it do? It creates H3O plus, and then it's game over, because once you have more H3O plus, what happens to your pH, guys? Significantly, right? However, if you have a buffer, the buffer is like, hey, acid, come over here. And so then the acid goes and it's like, and like attacks that. And by being diverted away from the water and to this weak base, that acid then spins around and turns into the conjugate acid of that weak base instead of H3O plus. So, guys, remember, do weak acids make a lot of H3O plus? No. So instead of getting the full force of the acid, you blunt it and turn it into the conjugate of the weak base that's there. Yes? Why don't you check? You guys see a baseball glove?
Yeah.
Right there.
Yeah. I'll throw it in the trash first.
Can you draw a diagram of how this works, Mr. White?
Be good. All right.
On the board.
Hold on. Yes, sir.
So essentially, you have a weak acid and you have its conjugate base. Separately, you add a salt that has its conjugate base as well.
Yeah. So
Okay,
now
which
we've got two separate sources of the conjugates from either
Yes.
side. It's
which causes it to, instead of go for HO or H3 or whatever, or for OH, it will go to the conjugate of the other base or acid.
correct. So let me show you an example. So as you can see here, guys, chiku, this is
Acid.
what household product?
Vinegar, acetic acid.
Vinegar. Okay. Now vinegar can dissociate with water a little bit and make H plus and CH3COO minus. But if we add some sodium acetate, because acetate is the conjugate, sodium acetate, what's the sodium going to do? Dissolve. And we're going to have lots of this CH3COO minus. And now this will get into a common effect situation with the acetic acid reaction. So now we have a scenario where we have plenty of acid because it's not enough to push this way because it was weak. But then we also have plenty of conjugate base. So now, if an acid comes in and tries to attack, which one is it going to attack? Is the acid going to attack this or this?
The acid will attack the conjugate base.
It'll attack this base, right? But here's the kicker. When it attacks this base, it doesn't have the chance to attack water, so it can't drop the pH very much. Instead, it attacks this, and what does it form?
Chiku.
Chiku, which we already know is, so in effect, you, at the system level, you're making it so that you're being attacked by a weak acid, not a strong acid. Now guys, What?
Can you still draw a diagram?
Hold on. You gotta learn how to draw things in your mind's eye first. Alright, so next. If I have a strong base, where's it gonna go? What's it gonna attack? Hold on. Morrow, pull the sword out of the stone.
The water? What'd I say?
No. Pull the sword out of the stone. Excalibur, come on. What is the strong base going to attack?
Water? I don't know.
No, we're in a buffered solution, so what's it gonna attack?
The strong acid you said?
Strong base. I'm adding strong base. What's it gonna attack on here? Can't attack water, right?
Right.
Because we got a buffer. But what's it gonna attack on the screen right now?
The H plus.
It's going to attack, because there's not very much H plus, because this pushed it back, right?
Right.
So what's the only thing to attack? This isn't here.
Na plus?
Only one thing it can attack.
Na plus?
Huh?
Na plus?
No, not gonna attack that.
You conjugate this?
What's that?
Conjugate this?
Base, you're gonna attack a base?
The weak acid.
Ah! The strong base is the only thing it can attack is the weak acid. Now, you did have a good insight when you said the H plus, because normally it would go after the H plus. However, guys, that's one of the reasons we added conjugate base, because what did that cause this one to do up here? So it gets rid of most of this. That's one of the reasons why we have to do it.
So that when it does attack it, doesn't.
It has to attack this.
Oh, okay.
Okay, so guys, if the strong base attacks this weak acid, we're not going to produce any more or very much more OH minus, because when a strong base attacks a weak acid, it doesn't make OH minus, it makes the conjugate base, right? And by making this conjugate base, have we produced any more OH minus? Maybe a little bit when it tries to attack water, but not very much. So, long story short, guys, buffers work by turning strong attackers into the conjugate weak whatever. So if it was a strong acid attacking, it gets turned into the weak
Base.
acid.
Right.
Because the strong acid attacks the weak base, right?
Oh yeah.
And turns it over here into weak acid.
Yeah.
What's up,
So
Bianca?
is this what's happening in salt and vinegar chips? So like if I were to like test the pH of salt and vinegar chips, what would it come out to be?
Probably low.
It'll just be no. This isn't what's happening because that's regular salt, like table salt. It's not sodium acetate they're adding to it. So to your example, if they were making the salt taste like salt with sodium acetate, you would be right.
But sodium acetate doesn't taste like salt. It tastes like burning.
Salt and vinegar chips.
So anyway, it's not sodium acetate. It is just regular salt in that example. No. All right, table salt. It's table salt.
Are we drawing a diagram now?
No.
Dang it.
All right. So guys, let's take a look at buffering capacity. So the ability of a buffered solution to accept protons or hydroxide ions. Guys, why do we call them protons? I thought they were H's.
Because it doesn't have just a protein.
H typically doesn't have, and so if we have an H plus, it's really technically a...
Proton.
And then guys, what is the formula for hydroxide? Now, go! No looking it up.
Always negative.
Okay, I'm impressed. My honors kids don't know it.
Your honors kids are honors kids. They're all stupid.
Hey,
I will throw shade at as many honors kids as I want.
Things get a little heated in here.
He said I don't
Alright.
care when I started talking.
So-
he called someone said he said
Hydroxide ions without a significant change in pH. So guys, let's kind of analyze this carefully. We're saying without a significant change in pH. Does that mean there's still going to be a change?
Yes.
Yeah, because you're still increasing a weak acid concentration or a weak base, whichever. And when you do that, you're still going to affect the pH a little bit, right? But it's a lot better than your blood going down to 3 pH, right?
Yeah. Wait.
I'm okay with going down from 7.1 to 7.05. That's fine with me. I'd rather that than go down to 3, which would be deadly.
Wait, hold.
Now, I
Don't.
guess the alien in the Alien movies, I guess their pH is buffered really low. Because when they get hit or whatever, they bleed out acid.
Yeah.
Hypothetically.
And it burns through all the different layers of the ship.
It tastes sour.
Yes. It would taste sour.
Yeah, their blood would taste like sour.
All right, guys.
You're
So
also
higher
not gonna die.
concentrations. Oh, guys, here's a new format we are learning right now. So, especially when talking about buffers, we will often refer to them as HA and A minus. So, guys, do you guys think HA is that going to be the weak acid or the weak base? Why? Because it's got. Okay, and then oh my gosh, this is gonna be so difficult. Is the A minus the weak acid or the weak base?
It looks like the weak base.
Okay,
It's a
so
weak
that's
one.
how it works, guys. When you see the conventions of HA and A minus, those are in reference to buffers. Buffers. So when you see HA and A minus, you gotta think buffers. And the HA is the weak acid, and the A minus is the weak base. So there's going to be more weak acid to react with the added OH minus, and there is more conjugate base to react with added H plus. The best buffers have equal concentrations of HA and A minus. Yes, sir.
Isn't A negative just a conjugate base?
Yeah.
So wouldn't that be strong? Because it's a weak acid?
No. Remember,
Oh, spectrum.
when we said that, it's like a spectrum. That's only true for like extremes, like extremely strong. We're not talking about those. When we're talking about buffers, we're exclusively talking about ones that are kind of in this range, not here and here. See, it's like a slider, and so we want ones that are like around here.
Okay. But if you have a strong, oh, that's why you can't have a strong like acid.
All right. So here it is, guys. Here it is.
Oh
Oh
god.
my god.
No. This is great.
No, this is not great. This is
like
was on the.
Mr. White.
this is significantly far from great
This
right
was
now.
on our test, and we didn't know what it was. It was talking about Henderson. Ugh. If only.
This is
What is
one of the coolest moments in AP Chem. This is the Henderson-Hasselbalch equation.
There was a
which
test.
you will notice is conveniently
what I'm
located
saying.
on your
Oh,
reference sheet.
Is one of the best
You
ones.
should
Has
have
to look
printed,
whatever
you
reference.
should have printed up the.
Okay, you guys want to know why this is awesome? If you can recognize what I've been saying, if you can recognize the hint, that it is a what kind of equation? Butler question, then all you gotta do is blindly whip out this, and you'll probably get it right.
Ooh, we're done with the lesson.
Let's go.
Is this on the
Well,
reference?
not quite, not
Lab
quite.
time.
Is this on the reference sheet?
It is on the reference sheet. It is on the reference sheet. The hardest thing though about buffers, guys, aside from maybe, as Michael was illustrating earlier, with buffers, it might take you a while to really fully wrap your head around them. The hardest thing though, aside from that with buffers, is the idea that if you don't recognize that it's a buffer, then you are not going to use what? This. And guys, is it possible to solve a question without this specific crazy equation?
Of course not.
No. So that's what makes them hard, is you can't just bungle your way through it like you could some other things.
Like
This
calculus.
requires a very special, it's like doing it in a video game. When you've got an enemy that's introduced at some point in the game that has a purple shield, And none of your weapons can penetrate that purple shield except for one special, unique one that's hidden on the other side of the map.
This feels awfully specific, Mr. White.
Yeah.
So you
This sounds like a
need-
very badly designed game.
Yeah.
So guys,
It sounds like
think of your
Pokemon.
Buffered Solution questions as the purple shield, and Henderson Hasselbalch is the special purple shield penetrating device. Yes, sir.
So it's the special purple penetrator.
You look,
Gotta love
that's a
it.
great question. Guys, how do you recognize it? You'll see in the question that they say, oh, we use this acid or base, and then you will notice that it's not in our big 6, therefore it is by default
Weak.
weak. And then separately in the question it says, we're going to add this salt to it. And that salt happens to contain the conjugate of the
Weak acid or
weak
base.
acid, then you know, or weak base, then you know, oh dear, oh jolly bee,
Better pull out the H&H formula.
better pull out the H&H formula and get a quick W on this question and move on.
You know, hold up. Hold up. I just noticed that like the abbreviation of this is H, like H line H, which is an H2 Lewis diagram. So I'm just saying.
Okay, so anyway guys, let's clean up a couple things first, because I know some of you nerds are gonna be like, ooh, what base is the log? Well, obviously, I have it spelled out right here, it's log, base, as almost everything else is until we get to LN. Okay?
Until.
What? Okay, so anyway guys, actually we've already done some LN, right? Like with the conversions, yeah. Alright, so these conventions are the main thing you have to be ready for. A and HA, are either of these going to be strong?
No, they're both going to be
They're going to be
weaklings.
conjugates of each other. And you know, because that A represents the common part, right? Okay, and the part that has the H on it is obviously which version?
The acid.
And the part without the H is obviously the
Base.
base part, okay? And so you put the base part over the acid part, okay? And you take the log of, and you keep in mind, these are concentrations. You take the log of this fraction, and then that gets added to pKa, and bam, you have a quick way of finding the pH. And then all the regular rules apply. If the question is weird and wants to know pOH, you would just take this answer and subtract it from
14.
and then do all the other crazy stuff we've learned. Yes?
Is there a specific reason why it has to be the salt specifically?
Yeah, it's because we hit on it earlier, actually. You guys, I'm actually like kind of heartened and proud of you guys right now. It's because it reduces the amount of the floating around H pluses or OH minuses by forcing the equilibrium of the original thing over to just, so then it's literally, you've got some of each, but there's no like H pluses or OH minuses to distract. That's why you have to add separate sources. That way it's just those two.
So that's why we learned about common ion as well. Because
Common ions, the ultimate application of common ions from chapters ago is this. This is a huge topic. This topic is almost always on the AP exam. Guaranteed at least a point or two on there. Yes, sir.
Is the H&H bros equation going to be on the sheets? That
It is
give-
on the sheet, yes.
Okay, good.
It's not labeled Henderson Hasselbalch, it's just like this.
Okay, I'm sure I can figure it out.
Yeah. Okay, so guys, here's where it gets kind of crazy, because you saw, what did this last very subjective comment say right here?
The best buffers have equal concentrations of HA and A minus.
Okay, so I call this subjective because this is subjective because
The best.
the word best, it should really say the easiest buffers. And that's because, guys, what is the log of 1?
0.
Oh! So if log of 1 is 0, and if you have the same of this and this, guys, what's 5 divided by 5?
1.
And what's the log of 1?
0.
Oh!
So is it-
then, if you have the same conjugates of each other, same concentration as your buffer, then as far as your math, it's really nice and easy, because if this whole thing is 0, then pH equals,
PK.
wow! Oh, and then you could, so wait, then we could always select our buffer based on something's published pKa value, because then if they're equal, the pKa equals the, so yeah, that's the trick. That's why buffers are pretty cool, because there's a lot of logic that goes into this, but basically, if you get the same concentration of both, then that's 1, and log of 1 is 0, and then pH equals pKa. So then we can use published pKa values to pick which one we want. Yes, sir.
Just a quick thing. The PKA, what is that like? What is that talking about?
The negative log of the Ka value.
No, but that's not what I was. Okay, the A. What is the PKA of? Like, which acid is it talking about?
Yeah.
Okay, so it's talking about the weak acid.
Doesn't Ka apply to the entire system?
Right. And these are both part of that system. So yes.
So I'm assuming you have to find that.
Yes, sir.
So, will we see that in multiple choice where they'll give us the same concentration and then they'll expect us to know that it is pKa?
Or like
They'll tell you to pick the best buffer for the situation. They'll say, oh, this situation needs a constant basic solution provided. And then it'll say, here's a bunch of buffers. And you'll see one of the buffers has a pKa of 10. And you'll think, oh, well, I want a pH of 10.07 or something. I'm going to pick that one and then modify it slightly to get 10.07.
Oh, okay.
We're going to get to the modified part in
Oh,
a
okay, so
second.
if they have the same pH, then is it not
Yeah,
the same
so,
concentration?
well, no, you usually will have a target pH that you want. And so you're going to pick something with a pKa that's close to it.
Okay, so the pK of the salt is important to what you
Right. So, pH equals pKa when the A minus equals to HA, because the log of 1 is equal to 0. So buffers made from very weak acids and their salts can have high pH values because they were very weak. So that's how you can get a buffer where the pH is around 10. Now, buffers made from stronger weak acids and their salts have lower pH values. So let's say you wanted something to stay at pH of 4, then you would use this. You would use a stronger weak acid and its salt, and you'd keep the pH around 4.0.
I have a question.
Yes,
Is this ever going to tie into titration?
this is critical. This is the only reason titration works.
So then, can we lab after this?
Well, I did get it started to set it up. See, I got the ring stands, I got the flasks
You told me that earlier, and then you said denied.
for today.
Oh,
Eh.
She's talking about next class.
oh. Can we like speedrun it next class?
So, if you guys want, the next class, we could make the solutions together and get ready for it.
Yeah, no, you lab when everyone's here. I like that.
Next class is PSD.
Oh, wait.
Next class is PSD, really?
Yeah.
Oh,
That's why I was trying to get it.
perfect. So, what we'll do, we'll speed run Acid Base 5.
No.
We'll speed run Acid Base 5. And
Let's not.
Yes, sir.
So how come like
This is kind of a stupid question, but the buffers, like, since they, like, kind of resist changing pH values, why is it that buffers, like, are measured by pH values?
Oh, no, they resist a change in it,
Yeah.
but every buffer has a different pH that it'll be close to.
Oh.
Like it resists changes. It plants its flag here. I'm gonna stay close to this pH. Another buffer is over here. I'm not moving from this pH. Because all things in life, whether it's life itself or this industrial process I want to do over here or something over here, you have different pHs, you need different cases.
That makes sense. Okay.
And remember we had the whole reactions we did in acidic solution and stuff, all sorts of things like that. All right, guys. So guys, here's something that kind of shows you the math behind how buffers work. Guys, if you've got a fraction and it equals 10, that means you have 10 times as much what?
A minus over HA.
The A minus, right? So guys, what that means is, if you send in, let's say you started where they're equal, right? Let's say you started where they were equal and you sent in enough base to just wreck this and make it so that, because what's the base going to turn HA into? The base will turn HA into the, because it's going to rip what off it? Hydrogen. And let's say you do that enough to where A over HA is now 10. Well, look, your pH is only going to go up by 1. But if you had added that much strong base to it, what would the pH have actually been if you hadn't had this buffer? Like 15 or 20, right? That's huge. But in this case, you would only go up by, okay, let's do another example. Let's say you added enough strong acid to make this fraction go down to 0.1, which means that you now have 10 times as much what?
Acid as base.
The HA, right? Well, look, your pH is only going to go down by, that's a lot better than becoming a negative pH, like a negative 5 pH, right? So instead maybe you go from 6 down to 5 instead of from 6 down to like negative 20 or something like that, okay? So does everyone kind of see mathematically the value of a buffer here? Like you could have a 10-to-1 ratio of attack and it still only makes it go up 1 or down 1. Is basically what's happening. So if you add small amounts of acid or base to a buffered solution, you could change the pH. You can make very small changes to the pH. And we can actually take advantage of that, because remember I said that earlier example? Well, maybe you want a target pH of 10.1. Well, this buffer is only 10. How can you make it go to 10.1? You can add a little bit more strong base to it, and you can actually cause the pH to go up a little bit to where you need it. Don't you guys love AP Chem?
You know, sometimes not as much as others.
All right, let's. Oh, by the way, before I move on, this has a typo on it. This is supposed to be a Ka value, but obviously, if it's 3.18, that is actually a
Incredibly strong.
pKa value. This is a pKa value that just got from here. Real quick. It's supposed to be. Supposed to be 6 times 10 to the negative 4. Okay, so suppose you are required to create a 0.5 liter buffered solution where HA and A minus have similar concentrations. Using the information below, select the weak acid and conjugate base pair that would be used to create a buffered solution with a pH of 4.8. So guys, this was obviously already, it's like, got ahead of ourselves here. This was already converted to what?
PK.
pKa, because remember, oops. Oh, here we go. If this part is 0, pH equals what? So we want to pick the pKa that's closest. So they just got ahead of themselves. It was supposed to be 6 times 10 to the negative 4. But first things first, we're going to convert both of these into pKa. So notice this one, which I have right here, it gets turned into 3.18. And then this one, we take the negative log of it, becomes 4.74. So guys, remember these values in your head. 3.18 and 4.74. Which one of those is closer to the target 4.8?
Second.
This one, right? So therefore, we're going to use which one as our buffer? Chaku, right?
Sure.
So does everyone kind of see how that works? We pick our buffer based on the one whose pKa is closest to the target pH. Yes?
I'm sorry, you were going like really fast and I was trying to write down the question. I still haven't written it down. Do you mind like just going on again?
Okay, so we're going to convert the Kas. This was obviously a typo on that previous slide. It's supposed to, this number. We're going to take the Kas and convert both of them into pKa. And the reason, the basis for that is if we can have the concentrations be really close together, then this cancels out and becomes basically close to 0, right? And so the theory is we can pick a buffer system based on their pKa being close to the target pH that we want. So we want 4.8. So we'll convert both of these into pKa and notice we get, Thomas, 3.18 and 4.74. Which of these two numbers is closer to 4.8?
4.74.
This one. So that means this CH3COOH is going to be the buffer we're going to pick because it has the closest value. Now, we can't just use a 50-50% of these because 4.74 is still not what, guys? It's not exactly 4.8, but we can figure out the exact amounts of each to use to get us to 4.8. So, question B here says, estimate the concentrations of weak acid and conjugate base that are necessary to produce an initial pH of 4.8 and prevent a significant pH change if 0.125 moles of NaOH are added. So, let's, we got to go back to the previous thing. What did we have up here? 0.5, and we have what down here, guys? So, first things first, we're going to need to whip out our precious
H&H formula?
H&H formula, yes. And you guessed it, we're going to plug in 4.8 as our target value for pH, and then what are we putting in as a pKa? 4.74. Welcome back, sir. And now, guys, can we solve for multiple variables? You can only ever solve for one variable. But what we could do is solve for a fraction. So when we have the log of this equals 0.06, we could take both sides as powers of 10, like 0.06 becomes a power of 10, right? And then, if we actually put 10 to the 0.06 power, we get 1.1. And so now we know that this fraction equals 1.1, which means the top is always how many times the bottom? 1.1 times it, right? So I'll give you guys a second to catch up, those of you who are writing. Guys, this is going to be a lot easier than it seems right this second, because you're going to solve all these the exact same way every time. Yes, sir?
Can you go back one slide real quick? So why is the C
acid and Ka different than the ones they gave us on this slide before? What's this number, Hobby?
6 times 10 to the x.
There was a typo on the previous slide.
Okay.
Thank you. All right. So, are we ready to move on here, guys, to finish the problem?
No.
Not yet? Okay.
How many moles do we want?
If I go back to the question, we're trying to protect against 0.125 moles of NaOH. That's what we're trying to survive. Because remember, NaOH is a strong base. So we're trying to figure out just how much of this buffer we need to survive that.
I'm sorry, Mr. Watt, are you bored?
No.
Okay.
That's right.
It's glad to know that you find this career fulfilling.
Oh, I almost used a bad word. It's like very, very, very fulfilling and amazing.
What was the bad word?
Yeah, what a bad word.
I would bet that it began with the letter S.
Can I go?
Darn,
Can I go to
it
the
was
bathroom?
darn.
Yes, sure, pass.
Darn. Gosh, jolly.
Gosh,
Oh,
Jolly.
folly.
It was
Alright,
heckin'
so-
amazing.
Here we go, guys. As I believe Michael was alluding to earlier, we are going to take the 0.125 moles of NaOH, and what are we going to divide it by to get a molarity?
Liters.
0.50 liters. So when those moles of NaOH are added, we will have 0.25 molarity NaOH. So this is what our buffer has to survive, and we've already found the ratio of these two that we need in order to survive it. So what we will do is we will plug in 0.25 for both of these, but we actually need to survive this, so we're going to actually change it. Instead of 0.25, what am I going to use? 0.26,
6.
because we actually have to survive it. So that is one of the little tricks of this. You can't just use this exact number that we figure out here. We use just add a little 1 to the final digit, make it a little bit bigger. And so that's how we get here 0.26 times 1.1, because remember we said it has to be a 1.1 ratio. 0.26 times 1.1 over 0.26. That'll give us 0.29 over 0.26, which we can confirm right here. Does this match what we had, 1.1? So that means we need 0.29. What goes on top, guys? The A minus, which is CH3COO minus, is going to be 0.29. And then the bottom one, CH3COOH, is going to be this 0.26. And that's how we find the concentrations of those two that we need.
Wait, hold on. I thought you said it was plus and minus 0.26 on the top and bottom. So why are we multiplying?
No, this is how much of them we need.
Okay, then can you back up a slide? I wasn't done writing stuff down. Right? Yeah, increases, decreases. Sticking out as 0 in the denominator.
Yes, sir.
So it doesn't match the original value, like the one that we got from A, which is like so much easier.
Right. Yes.
Where did the 0.26 times 1.1 come? Like I was following.
Right here. 0.25 is how much NaOH is bearing down on us, and we have to be able to survive it. In order for the buffer to work, the two values do have to be somewhat close to each other. So we are going to use that 0.25 for both of these. However, we actually need to fully survive it. Because if even one drop of NaOH makes it past the buffer, the pH is donezo. So what we do is we fudge it a little bit and make it 0.26 instead of 0.25.
Is that scientific terms, fudging?
Well, it's all about survival, so yes.
Okay.
Like, system is still alive. That's what matters. So maybe it's less science and more engineering.
So do we just like round it up to like 0.10, like 1/100th above or below? I would suppose. What would
Yeah,
that
that would
mean?
be acceptable as well.
Okay.
But typically, you just want to add a little hash mark to the end of whatever you have.
Got it.
Just to what you're just it's like you're engineering it to survive attack from NaOH. Okay. Now, is anyone confused as to why we say increase and decrease and why they're both positive?
Yes.
That's simply because for a buffer to work, you need to have both. So if we need this much, if we need this much to survive, then we need this much to kind of balance it all out.
But we were taking it away.
No, it gets taken away when it gets attacked. Prior to the attack,
Oh, okay.
Prior to the
Okay.
attack, it has to be equal to each other.
Okay.
Like equal-ish, 1.1 ratio.
Would it make a difference if you do 0.25 instead? Because I know you said it has to be slightly more, so it's not 0 in the denominator, but like, what, let me see.
So in order to stay at the exact pH range we want, it is important to do that fudging on the number.
Yeah, because like,
Because otherwise, if you get to 0, you're right that that's undefined. But beyond that, that means that your pH would be controlled solely by whatever survives and not our targeted buffer pH.
that makes sense. Okay.
And so like even one drop in NaOH could just skyrocket the pH.
Yeah.
All right, guys.
Oh, another one.
Let's combine polyprotic acids and buffers. Yeah.
It's been too long.
Wait, what am I looking at? A polyprotic system.
What's
the,
it?
the
It
three
gives
different
you all the
reactions where you take away an H.
Oh, is that one? Oh, God.
It gives you the pKa's already though.
Yeah. See? As Charles points out, it gives us the pKa, so we're already chilling. Let's read the question. Suppose you are required to create a 1.35 liter phosphate buffered solution with a pH, that's why they have the 3 phosphate reactions, with a pH of 7.29. Select the weak acid conjugate base pair that would be used to create this buffered solution. Ladies and gentlemen, it's possible to make math errors and it's acceptable, it's okay. Is it allowed? Am I allowing you to get A wrong?
Yeah.
No one in this room is allowed to get A wrong. Look at it.
What if I get A wrong?
Which one is so clearly the answer to A?
It's obviously the
Go
first.
ahead, Daniel. The second equation.
So it's not the first one?
Conjuring up Yoda when his heart hurt during Order 66.
Guys.
Guys. Right here. 7.21, 2.12, 7.21, 12.32. Which of these three numbers is closest to 7.29?
7.21.
7.21. Is anyone allowed to get A wrong?
Yes.
No one is allowed to get A wrong. You pick the one with the pKa closest. Okay? Estimate the concentrations of weak acid and conjugate base that are necessary to produce initial pH of 7.29 and prevent a significant pH change if 0.45 moles of strong acid or base are added. So guys, it's gonna be just like we did before. Now that we have our pKa, we're gonna use the what equation?
H and H.
Henderson-Hasselbalch equation, which is on your reference sheet. Now, ladies and gentlemen, after we've done that, how are we going to find the concentration of strong acid or base? To find the concentration of strong acid or base, we'll take these 0.45 moles and divide it by 1.35 liters. And then what do I have to do to those molarities before we can use them? I gotta inch them up a little bit, right? Okay, so we all agree on this one, right?
Yeah.
We all agree on part A? Let's look at part B now. Or do you guys still need part A real quick for writing? Does anyone still need an answer for part A? Okay. Part B, we're going to find the ratio of the concentrations we need. We're going to use Henderson-Hasselbalch. Guys, what am I putting in for pH? 7.29, right? And then what was our pK we're using?
7.21.
7.21. Okay? Guys, how do I solve this?
Well, you subtract 7.21.
Subtract 7.21 from both sides. Okay? And then how do I move on?
10 to the 0.08.
10.08 and then 10 to this, which crosses out the log. Okay, and that gives us a ratio of 1.2. Interestingly, guys, whenever it's greater than 1, that means which one is higher? The numerator, right? So just keep that in mind, guys, that the numerator is the one you're going to multiply times 1.2. Yes? Yeah, go ahead. All right, guys, right. So we can learn here.
Do you see how the mood increased? You're like, right. So we can, and then someone's like,
I think everything is great.
I feel like that's a biased
I'm
opinion.
in denial, guys. Don't worry.
Hey, what's up, Manish? Which part? Oh, we're gonna do that on the next slide.
No, who makes these equations? Who sits around for 20 years and figures
And then we're gonna put that in both. We're gonna multiply
I wonder how bad their family life was.
All right, guys, here we go. Shh. So, guys, as you can see, we're gonna take the 0.45 moles and divide it by 1.35 liters. That's going to give us 0.33 molarity. But guys, are we allowed to use exactly 0.33?
Nope.
No. What am I gonna get up to?
0.34.
We're gonna use 0.34, and then we're gonna plug those in. This one times 1.2, and this one here. That'll give us a ratio of 0.41 to 0.34. And then if we divide these just to check, look, is that 1.2? Okay, so then the HPO42 minus will be 0.41, and the H2PO4 minus will be 0.34. And that's a wrap.
Oh, that's it? We're done?
That's it, that's done. Now guys, listen, this seems tough at first. But that's what I'm telling you. You gotta listen to me here. It's literally this exact same process every single time. Boom, 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 boom.
Are there any
What
more
about
acids and
when they-
bases? Are there any more acids and base units? Like lessons that we gotta go through.
Titration.
Are we doing a lab soon?
Yes.
Are we doing it on the PSD day so we only have 55 minutes instead of the whole
No,
hour?
we'll
and a
probably
half?
just we'll burn through acid base 5.
But doesn't that take a long time?
No, it's just titration.
I
You're
thought
just
that.
adding enough of one to exactly equal the other one, and you get a color change, and boom,
There's
it's
a
there.
catch.
That's it. I just summed it up in 2 seconds. Ooh, we're gonna add, and it's gonna change color, and we stop, and now they're equal.
Mr. White, did you have coffee this morning?
What's that?
Did you have coffee this morning?
No, I'm just really angry today.
Why are you so angry?
Huh?
Why are you so angry?
I'm so sorry.
You know what? I've got various things that are making me angry these days.
You know, I
You know, I'm not
One
a
of
trained
them is you.
psychologist, so I
You
don't
guys
know how to
actually
help
make me happy.
Huh?
You guys make me happy,
Like,
Mr.
I
Matt.
have a pickup line. I have a Chem pickup line. An acids and bases pickup line.
Oh, hold on.
Okay, you can use this on your girlfriend.
Okay, hold on. I'll text it to her right now. Let's hear it.
Okay.
Do you need this? throughout the day.
Okay, hold on. Okay, I'm ready.
If I'm a
It just
base,
didn't charge for like half
then
an
you're
hour.
a strong acid because you make
It
me
just- It
weak.
just didn't charge.
Good job.
If-
I'm a
Thank
conjugate.
you! Aw, come on, guys.
It wasn't.
If I'm a base, then you're
Wait,
a
wait,
strong
is this the last
acid
one?
because you make me
No, we're not
weak.
done.
But like, doesn't work that well.
If
Only conjugate acids make sense.
it's better than calling it a basic.
Okay, yeah, it's true.
If I'm a base, then you must be a strong acid because you make me weak. That was good, right? Mr.
Okay, I modified it slightly.
What?
I modified it slightly. Okay, I'm sending it. I wrote it like this. If I'm a base, then you're a strong acid because you make my knees weak.
Okay, that's cute. And what'd she say?
I mean, I literally just sent it.
It was like 10 seconds ago. Calm down, Victoria.
What about Mr. Mack? I can send it to him.
Mr. What?
Yeah, send it to Mr.
Oh,
Mack.
she texted me back. I love you. Wait, with the U instead of the Y.
Wait, let's overthink as a class.
Wait, I thought you said we were done.
No. We got more. Okay.
We're just over halfway through.
Okay, so how many
Very
moles
sad.
of NaOCl must be added to a 650 milliliter solution of 0.50 molarity HOCl to create a buffered solution with a pH of 7.5? So our Ka is 3.5 times 10 to the negative 8. Assume that the volume does not change. Okay, so guys, first off, we're going to find the H plus that we need to make a pH of 7.5. So, guys, all we got to do is take 10 to the negative pH, 10 to the negative 7.5. That tells us that we need an H plus concentration of 3.2 times 10 to the negative 8.
Whoa, slow down, man. Give me a second. This is an entire slide. I gotta write this crap down.
Okay. Oh, wait. Hurry. Hurry.
So this is just the same thing again.
Yeah, let me just give you a preview real quick while people are writing.
I'm gonna use it on Gabby.
So, like, this one's about just mainly about how you prepare it.
Okay.
So, the previous ones were about calculations and stuff. This is about literally getting them together to prepare.
Victoria, you should use it too.
Mr. White, you won't sleep.
No.
Ryan forgot what KA was.
What is going on?
What?
Disgusting.
Okay, thank you. Exactly. We'll believe it.
I went through
That's how
everything.
I don't know why it's called that.
I went through like
Freaking Gianni has all the time.
No, it can't be.
It's called CBT.
Yo, Mateo, he hasn't played that in ages.
What is that?
He hasn't played it in ages.
Why is it called that?
Because it's the super people.
Why is it called CBT? It's called CBT. I'll say it louder.
Yeah.
Bro, why is it called that? I don't get it.
PvP to Rebecca.
I don't get it.
You like plug in the one time.
And what happens when
I don't know. It was something like that.
Alright, I hear a lot of talking, so we're moving on. So guys, now, we're gonna find the number of moles of NaOCl here, and we're gonna take the 0.65 liters, we're gonna multiply it times the molarity, and that's gonna give us 0.36 moles of NaOCl. So guys, this is how we can create one of these buffered solutions. That's what example 3 is all about. And so our final thing is
This is a buffed
0.36 moles
solution.
NaOCl.
Look at that question.
Yeah,
Alright.
it's buffed out.
Buff.
Alright guys,
it's
so
a strong boy.
as you guys can see, the basic premise of buffers isn't as scary as it may sound at first, but there are different ways we can explore it. Like here, guys, like here, we're looking at how we could prepare one with the two parts, the HA and the A minus. All right, give you guys a couple seconds here.
I
So
say
Mr.
you watch
White.
the crash course.
Mr. Wade.
Are there crash course videos for chemistry?
Yes.
Yeah, is there what?
The buffers one is really nice.
Yep. Highly recommended.
Is there what?
In fact,
Can we watch it?
we'll watch it after we finish.
Yeah.
What?
All right, what's up, sir?
So since we had a homework day on Friday, when is our test?
Oh, Albie, that's a great question.
No.
I'm not. Fourth quarter.
No.
Excuse me? No, we're not finished.
No, I need it for this one.
I need to.
Yeah, no, it's this quarter.
No, don't put it this quarter, please.
What are you guys talking about? It's absolutely this quarter.
Perfect. I'm at an 80, shut up. I want to be at 80.
So guys, let's explore some things here about pH and the AHA ratio. So comparing pH to pK for any acid solution, buffered or not, will provide information about the A to AHA ratio. If pH is less than pKa, the acid form has a higher concentration. If pH is greater than pKa, the base form has a higher concentration. Nifty information to know. Okay, so let's do an example. A buffered solution is created by mixing solutions of HCO2H and NaHCO2 at 25 Celsius. The final pH was measured to be 2.89 and a Ka of 1.8 times 10 to the negative 4. Which species has the highest concentration? So guys, first off, before we do anything else, are these conjugates of each other? Ignore the Na.
Yes.
Yeah.
So HCO2, HCO2, right?
Yeah.
Okay? So that means, by default, this is a what type of problem? Which means we can look at its pKa. So pKa is the negative log of Ka, so we'll take the negative log of 1.8 times 10 to the negative 4, we get 3.74. And so then here, that pH that we wanted here, to pH 2.89, is going to be less than pKa. So if we go by this slide right here, when pH is less than pKa, then the acid form has a higher concentration. So the acid form is higher. The silence is deafening. I'm so happy right now. Stop trying to derail me. But yes, I did, and it looks amazing. I'm excited. I want Fue Coco, of course.
Yes. Duck Boy too. Duck Boy
I will admit a little bit of disappointment and fear, because when I saw it, I was so sure we were going to finally get a fire-breathing Tyrannosaur Pokemon.
No,
But instead, it says in the Pokedex, it says a croc.
Isn't it Gen 9?
Dude, he's gonna be a ghost pepper. Think about it. The white part on his head is a skull. He's shaped.
Well, I don't
like a
care. It could be Ghost Pepper, but it should have been a
Ghost
T-Rex.
fire type.
Instead of a T-Rex, we're getting a crocodile.
Ghost.
If it's a pepper, wouldn't it be fire grass type or fire plant? I don't know. Food type.
Pepper would be a very interesting fire gas.
No, it's confirmed.
It would burn itself.
Spain / Portugal.
It's a new
All right,
food
guys,
type.
move on here. Hydrobromic acid is added to a buffered solution containing acetic acid and its salt. Write the net ionic equation for the overall reaction. Guys, I know you guys love net ionic equations.
Yeah.
So guys, hydrobromic acid is HBr. Guys, is HBr one of our strongs?
Yeah, he's gonna give me all the games.
Yes.
It
Yes,
actually
it is.
Yes.
So, guys, HBr, since it's strong, is going to be represented as
that.
H3O plus, right? Now, why are we showing H3O plus attack acetate? I thought it said it contained acetic acid.
Yeah.
Oh, so it's attacking the,
So,
because the salt can accept a what from here? An H plus. So guys, what's this gonna turn into?
it's gonna be cuckoo and
Chaku, right? And H2O, guys, for the sake of our pH, we would prefer it become Chaku and H2O versus having full power what hitting us. Right, so that's why buffers are amazing. Okay, now here's another example. Sodium hydroxide is added to a buffered solution containing hydrofluoric acid and its salt. Write in that ionic equation for the overall reaction. Guys, sodium hydroxide, strong or weak base?
strong. Strong base.
Strong!
Because it's
The most famous
weak.
strong one. The hesitation is scaring me, guys. Alright, so HF, hydrofluoric, is that weak or strong?
It's weak. It's a weakling.
And then if it's mixed with its salt, that means this is a... Okay, so someone tell me, what's the reaction to this going to be? Without cheating and looking ahead. What is the reaction to this? What does that NaOH turn into when it hits water?
Dissolves.
It breaks down into the hydroxide and the
So
sodium.
it's hydroxide.
Oh,
Okay,
yeah.
so NaOH will be OH minus, alright? And then which one is it going to attack? The HF or F minus?
This salt, right?
Oh, HF since it needs the H plus.
Oh, yeah.
Good job, sir. Alright, what do you guys think of that one?
I think we should watch the crash course now.
Yeah.
We will, we're getting to it.
Yeah, but
We're
like,
getting to it.
let's get to it
Watch
faster.
it at the beginning of the class.
Alright,
Wait,
so...
Can you go back to?
No, I can't write this down that fast, man.
Just type it.
I can't type
So
into a
is this
notebook.
kind of like it's saying like how to write the reactions?
How to write the reactions,
Okay,
yeah.
that makes sense.
Because with buffers, it's not just about the math, it's also about being able to do this.
Yeah. Okay.
And like this could be like one of the steps in a free response problem
Yeah.
is write
Write
the what will actually happen, because see there's several different options.
Yeah.
Okay guys, here we go. Let's look at solubility in strong acids. The solubility of slightly soluble salts containing basic anions increases as H plus increases. Basic aqueous anions will accept protons from the acidic solution. Here, we're going to add a strong acid, and that strong acid is going to attack what, guys? The OH minus. And so, guys,